All right, so the last section here on factoring polynomials, factoring trinomials, is some special cases, and we talked about some special cases when we were multiplying, right? And when there's a sum and difference product, or if we're squaring a binomial, then we can shortcut our way into multiplying those guys out. Well, same can be said about factoring. There are two special cases that, if we recognize them, we can factor down much, much quicker. And those two special cases are exactly what they were for multiplying. They come about when there's a sum and difference product, or if we're squaring a binomial. And when we have those two special cases and we multiply everything out, we come up with one of two different things: either the difference of two squares or a perfect square trinomial, and that's what we need to recognize and be able to factor. Okay, quick review. Multiply these out real quick. You should get this: x squared minus 9 and x squared minus 25. Okay, if we FOIL or double distribute, however you want to look at it, that's what we get. Okay, it's also that sum and difference product in our shortcut: square the first, square the last, and stick a minus sign between them. Okay, two different ways to approach it. Now, so if we think about this, when we have what's called a sum and difference product, two binomials that are exactly the same, only one's addition, one's subtraction, then we can shortcut our way into squaring the first, squaring the second, and sticking a minus sign between them. But the object here is to be able to go backwards. We want to be able to go from this back to this. Well, first thing is we have to recognize this, okay? And here's how we do it, right? How do we know that we're looking at the difference of squares? That's what this is called. The product, a squared minus b squared, is called the difference of squares. Well, here are some things to look for. First off, it's the difference, so we need a minus sign, and of squares. So our two terms need to be perfect squares. Now, what are perfect squares? And you see some examples down there. 16 is, because the square root of 16 is 4. 25 is, 121 is, 625 is, because you can square root those numbers and get a whole number. X squared is a perfect square, right? Because if you square root x squared, you just get x. All right? So if we have a difference of squares, then the way we factor this down is we square root each term, and we make that our terms in our two binomials, and we do a plus or a minus. Okay? So let's get into an example to make more sense. So things to look for: two terms. Anytime you have two terms, the first thing I look for is a minus sign. There has to be a minus sign. And in this guy there is. And if that's the case, then we try to square root each of the two terms. Square root of n squared is n. The square root of 36 is 6. So this is a difference of squares. So we make our parentheses. We put n here as the first term, 6 here as the second term, and we plus or minus. And we're done. Okay? It doesn't matter if you go minus, plus, or minus. It's still the same thing. Okay? As opposed to this guy, okay, which we cannot factor this way. Why not? Because this is not a difference. There are two terms. Each term you can square root, but it has to be a difference. So since we can't factor this using that shortcut, it turns out we can't factor it at all. It's prime. Okay? So try your hand at this guy and see what you come up with. Stop the video and then start it back up and see if you're right. And did you get x plus 5, x minus 5? It's two terms, difference, square root each one of them. And so x and 5 are your terms in your binomials, and you have to plus or minus. Why do you have to plus or minus? Because if you were to multiply the outs and the ins, right, or the smiles, then they would add to 0. And that's why we're missing this middle term. We're missing a third term. We're missing the middle term. That's why, because the 5x and negative 5x would add to 0, and so we don't need the middle term. Okay? So that's why we have two binomials here, because we have to create these opposites for the middle terms, the 5x and the negative 5x. Okay? All right. Here's one that you're going to have to think about for a second. It's two terms. It's a difference. But you cannot square root and get a whole number for 24 or 150. It's a little bit of a problem, but you have to remember, we have always said from the very beginning of factoring, the very first thing you look for when you factor is a greatest common factor, which for here turns out is 6. You factor out a 6, you get 4m squared minus 25. Okay, now check for your difference of squares. Two terms, subtraction sign. If you square root 4m squared, you get 2m. You square root 25, you get 5. So you create your two sets of parentheses, 2m here, 2m here, 5, 5, plus, minus, and we're done. Okay, that's it. It's pretty sloppy, but that's it. Fix it here. Okay? So we still need to be in the habit of looking for a greatest common factor first. Okay, try this guy. Stop the video, start it back up, and see how you do. Did you get 2x plus 7, 2x minus 7? Okay, hope so. You can see there the square root of 4x squared is 2x, the square root of 49 is 7. This is a difference, so we're ready to do the shortcut. Okay, one more for you. Try that. Stop the video and see how you do. Okay, did you factor out a greatest common factor first? There is a GCF of 8. And so when you factor out an 8, you end up with this guy here, x squared minus 4y squared. It's two terms. We're subtracting. The square root of x squared is x. The square root of 4y squared is 2y. And so we can create our two binomials like this. Okay? Make sense? If not, make sure you come find me. All right? Now, the next special case is what we call a perfect square trinomial. Okay? If you remember, if we squared a binomial, okay, it's the same thing as writing it out again and foiling. Boom, 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 boom. Okay? When that happened, there was a shortcut to multiplying them out. You square the first, square the last, and then we do u times 2, which is this middle term here. Okay? In other words, if you did something like x plus 4 and you wanted to square that, okay, then you could write this out twice and double distribute. Okay? So here and here, and you get x squared plus 4x plus 16. But if you remember, those two middle terms were always the same. Okay? Because x plus 4 times x plus 4, the outs and the ends were always the same. Okay? That's the difference between this situation and the difference of squares that we just saw. There was no middle term in the difference of squares because those two, the outs and the ends, always added to 0. Here, the outs and the ends are the same. That's why we can shortcut this. We can square the first term, square the last term, and then take u times 2, x times 4 times 2, and get 8x. Okay? So that's how we shortcutted squaring that x plus 4. Again, the purpose of this is to be able to take this trinomial and work back to this. We need to go backwards. We need to recognize that when we have a perfect square trinomial like these guys, that we can actually factor it down into a binomial squared, one single binomial. When we're factoring a perfect square trinomial, we're looking for one single solitary binomial that we're going to square, not like the the difference of squares that we were just doing, where we had to create two different binomials. Okay? Now, how do you know that you have a perfect square trinomial? Well, the first and the last terms have to be perfect squares. We have to be able to square root them and get whole numbers and all that kind of stuff, just like we did with the difference of squares. But the difference here is there is a middle term. And the middle term has to come from being twice the product of one factor from each of the first and the last terms. That's a lot of words. So let's take a look at one. So for example, x squared plus 10x plus 25. Okay? How do I know that this is a perfect square trinomial? Well, because if I square root this first term, I get x. If I square root the last term, I get 5. I get 5. Now, if I take these two, x times 5 is 5x times 2 is 10x. And so it will give me that middle term. So I know that this is a perfect square trinomial, and I can factor this down into x plus 5 quantity squared. Okay? So let's try. That's the first example that's really not in your notes, but here's another example, right? So you have to know, you have to recognize, is this a perfect square trinomial? And this is going to be, the perfect square trinomials are going to be harder to recognize than the difference of squares, right? I'll give you a difference of squares in here really quick. X squared minus 81 is a difference of squares. And the x squared minus 81 is going to jump out as a possible special case because there's no middle term. And that's the biggest thing. There's no middle term and a minus sign. Okay? Here, there is a middle term. So it's going to look like any other trinomial that we have to factor. So what I would do if I were you is I would get in the habit of checking to see, right? And you can do it quickly. Can I square root the first term? If the answer is yes, then you might have a perfect square trinomial. Can I square root the third term? If the answer is yes, then you might have a perfect square trinomial. Now, if I take this guy times 2, 9 times x is 9x times 2 is 18x, it does give me this middle term. So I know that it's a perfect square trinomial. I close down my parentheses, I make this a squared, and I bring this sign down with me as an x minus 9 squared. Okay? We didn't talk about that with the last slide, so I want to show you this real quick. Okay, how do you know whether to use a plus or a minus inside the parentheses when you're squaring it? Because you're only going to use one, because you're only going to have one set of parentheses. And it always comes from the term, from the middle term. What's the sign on the middle term? If it's plus, then you're adding. If it's subtracting, if it's minus, negative, then you're subtracting. Okay? All right. Try your hand at this one. Stop the video and see how you do. Okay? Have you gotten this far? If you square root the first term, you get x. You square root the last term, you get 3. Now, if I take x times 3, I get 3x. Times 2 is 6x. So I am getting that middle term, so I'm going to square this binomial, bring down this minus sign inside of here, and we're done. Okay? Awesome. Now, look at number 9. First things first, I'm going to check to see if this is a perfect square trinomial. Can you square root the first term? The answer is no, because you can't square root 3 and get a whole number. I mean, you can square root 3, but it's not a whole number. That's what we're looking for. So we got to stop for a second. Well, remember what we're always supposed to be checking for first, and I keep forgetting to do this. But you're always looking for a greatest common factor first. So we can factor out a 3 here and get z squared minus 8z plus 16. Now check for your perfect square trinomial. Square root the first term, and you get z. Square root the last term, and you get 4. Z times 4 is 4z, times 2 is 8z. So we do get this. So we square here, bring down your minus sign, and we're done. Okay, so check for that GCF first. Try this guy. See what you come up with. Stop the video, start it back up, and see how you do. And you should have gotten 2n plus 5 quantity squared. Because if I square root 4n squared, you do get 2n. If I square root 25, you do get 5. And 2n times 5 is 10n. 10n times 2 is 20. So this is a perfect square trinomial, and so you factor this into 2n plus 5 quantity squared. Don't need this step. Okay? Another one here for you. Give it a shot. Stop the video. Start it back up and see how you do. Did you get 4y plus 1 quantity squared? Square root of 16y squared is 4y. The square root of 1 is 1. So we're in the running. 4y times 1 is 4y. 4y times 2 is 8y. So this is a perfect square trinomial. And so it factors down to 4y plus 1 quantity squared. Okay? Another one here. It's got a couple of variables in it, but it doesn't matter. It doesn't change the process. So give it a shot. Stop the video. Start it back up and see how you do. And did you get 3a minus 7b squared? Right? The square root of 9a squared is 3a. The square root of 49b squared is 7b. 3a times 7b is 21ab times 2 is 42ab. Okay? Hopefully this is making enough sense and makes your life a little bit easier if you can recognize these two special cases. Okay? Homework's out in Canvas. Give it a shot. See you guys next time.